Okay, everyone. Um, so first, I think all the homework from homework 1 to homework 5 have been all graded and released. So let me know if you so you're confused of any grading, and also so please request a regrade if you find any mistakes. So as I said, some of the homework solution have multiple, actually have some of the homeworks have questions have multiple solutions. So it could be possible that the TA may, so the grader may misunderstood your solution. So please regrade if you think your answer is correct. And also we should also release all the solutions to homework 1 to 5. I think those solutions will help you to review help you to review all the knowledge so far and prepare for midterms on Thursday. So any questions about the homework and the midterm? Okay. So and also I want to just quickly tell you there is a typo for midterm 5. I think that's homework. So that should be. So there's a the previous solution was not correct, so we found it, and I think it's already the correct solution has already been uploaded to the Canvas. So in homework 5, exercise 7, the first solution is correct. The second one, because you have a so this is a defective matrix. You have two eigenvalue, -0, -0, and it's a defective matrix. So you can now, so when you compute the EAT, you need to use the Cayley-Hamilton method. So I think that's just a regular, similar to what we did before in the previous homeworks, but I think the solution was wrong. And we check it and we uploaded that to the Canvas. I think all the homework were graded with this correct solution. So that's, we found this this weekend, and we are already updated. Okay. So another one is please try to test your VBOT simulator. I think that will be very fun. So you'll probably see a lot of, I think another fun part is you can see a lot of examples in MATLAB, in Python, in C++, in C, how to control a release the robot simulator. So do you guys, if you can show me in the chat, so have anyone already tested the VBOT on your computer and it runs? So I just want to know that you guys are already started to play with it. Have any of you tried VBOT? Okay, and you think that's it's running, right? So it's quite fun. Yeah, great. So thanks. From right after midterm, we'll start to use this VBOT. So please try to do that as early as possible. And it's a test for your computer, whether your computer can support it. I think if you have some computer with say 2 GB memory, so that will be very slow. But as a regular like middle level computer, it should be fine. Like a Dell, any Dell, what is a PX? What is a name of the Dell computer? Or any Lenovo middle level computer should be able to run it. Okay, so let's review and this what we did in our last lecture. Okay, so we have, great, so this is a review in our last lecture. So we learned what is PID. I think this is a super important concept, and I hope you can know the inside out of this algorithm. So basically, you have something you want to the reference. That's like what you want to, how you want to control your output. So you want your y t go to say your reference t. Okay, so that's our goal. So if that's our goal, then we compute the error between them. So this is our error, et. Okay, so that's our error, and we feed the error. So we feed our error into the system. We feed our error into the system. Sorry, I think to set the system again. One second. Yes. Sorry for there's a technical issue. Magic keyboard. Okay, it should work now. Good. Okay, so you feed the error into the system. So this is Y, this is R, and you have ET, and you calculate. So basically, you can directly feed back the ET into the plant. The plant is input is our control. So this is basically here. This is our controller. This is our controller, right? The controller output U. Actually, I should say this R is also inside the controller because that's how we compute things. So this is our controller. So we use sensor, the input is Y, the output is U, right? The output is U. So U is our command, and our input is Y. Y is from some sensors. So this then we gave the command to some actuators. Right. So then this what is inside this blue area, this blue zone is our controller, and we have this error. We can just give again, just time a value to the error and directly put it back to the plant. So this is called P control. However, we know that P control you can now, when you are close to, when the error is small, like in the driving example I gave in the last lecture, when you close error small, you can now eliminate the error because you don't have enough. So the E will be too small when you're close to your value. So you cannot never reach R, right? So when you reach R, this E is 0, so you don't have any motivation to, when you're close to R, the E is too small. So this KPE is also small. So you don't have enough momentum to drag the input, to drag the plant to Y, to output Y. So that's why we have integral, so that you can integrate things, so that when you are close to R, you still have your history. That's a debt you need to pay back to drag the system to R. However, this debt could be too heavy sometimes. So you need predict it into the future. So that's your derivative of E, and give a gain of KD. Then with this one, you can damp out with the KI, you can increase the speed. With the KD, you can damp out the sum of the overshoot. So with this combination of these three things, you can control the system. right? So and make the output to be desirable as RT. So this is a PID. And also learn the problem of PID is first you need to hand tune KP, KI, KD. Sometimes you cannot hand tune the system. For example, like when you launch a rocket, you don't have that to tune, right? So this is not a model based. This is a tuning based on trial and error. So we want something like what if we know more about this P? So in this case, PID, we assume that the plant is a black box. It's more like a black box method. You just automatically tune it. And but what if you know more about this P? For example, P is a plant that's a linear that I can use the say A, B, C, D to represent it. So what if you know this knowledge? If you know this knowledge, things become, you can do a little bit better. One thing is you can design K directly, and you can not only drag these things back, you can also control how the speed precisely use the eigenvalue, and also you can have a multiple input and multiple output. So this is what we learn in the pole placement method in the last lecture. So we gave a single input, single output like example, but we can actually do multi-input, multi-output. That will be the end of this sum module. So basically what you do is, okay, so you have a, here I take the state out of this P plant. I take the state out of this P plant. I give it back, and the time again, this gain now is a matrix. So this gain is now a matrix. And I put this matrix times this states, and I compute this our input to the plant. So this is our command. So basically here, this guy is our controller. So this is our controller. Okay, so this is our controller, and you can see this is actually very similar just to a P control, because what you do is just, if I do some very subtle multiplication, for example, I say, okay, here I don't have a first, you see it, I don't have a reference. You could have a reference, but just make this to be the similar, like consistent. You can have a, say, 0, right? So that's a 0 is what you want to do, and here is a plus or minus. Just write similar to what is on this side, right? So this is what you have, and this is what you have, and then we have because we have a minus, this minus sign here, so now the K become minus K. The system is still the same. So you have a minus, you have a 0. You can make it back, put it back. So so when probably you will ask, okay, so what about R? What if I want to control things that are, just to not here say basically you want to control your reference is 0. You want just control the state to be 0. In other words, you want to bring your state to the origin, right? So, and you just by times a minus k, which is your P gain, and you just put it back. Okay. So because this K is a matrix, and your X is a multidimensional, so actually this system is much more expressive than this. You can emulate the PID easily with this system. Okay, because X can be, say, derivative. You remember we can have X to be derivative and a double derivative, double dot, the x1 dot, x2 dot. You can just put into the states, right? And I think we practice that. In that case, the A will be 0, 0, 0, 1, and 0, 1, 0, 0, 0, 0, 1, 0, 0. So that will be easy to implement in this case. But you may also mention why we have 0, right? So what if I want, instead 0, I want it to be RT? You can, that's actually similar. You can use a similarity transformation, or just make your RT, shift the RT to the origin, right? In other words, if you want original, you say, okay, the original system, I want to bring xt to 0, right? So that's original system. And what if you say, I want to bring my not 0, this time I want to bring to RT. So what you can do, you can define new state space equation that your x dot just t will be xt minus RT, right? Then what you need to do, you still need to do, what you need to do is you just bring this x tilde t to 0. Right? So then you just compute the a tilde, b tilde, c tilde, and d tilde, and you can use a similar method. In other words, in this case, this x is more like this, if we imagine this as e, so this is more like an error between your real state and your reference, right? So that's your real state and the reference. This is what so you basically use that to define your state. That's your new state x tilde, and you have a tilde, b tilde, c tilde, you can still do the same. Okay, so any questions so far? I think it's good to know the math, but it's very important to see this picture and understood that we are now doing something different than PID. We actually only do P this time, except we augment the states so that those states will represent the derivative and integral automatically. Because derivative and integral, they are linear operator, right? So if you remember how when we started the transfer function or Laplace transformation, that we prove actually derivative is actually a linear operator. Okay. So if no questions, let me give you an example. Just again, so in the project, I would say you just do this with your computer. Don't do this by hand. But this is still a simple example with this. You can see this is a simple parameter, 1, 2, 3, 4, 5. So the purpose is now to say how to derive this. This is supposed to be your requirement before the midterm. But I just use this 2x2 example to illustrate what is the pole placement. So let's do this together. And maybe this also can help you a little bit to prepare the midterm. Okay, so the question is this. I have a system, okay? So this is our A, this is our B. And I want to, so this system, whatever this system is, I just want to say after I do this feedback control. So I just, so I have plant, this is a plant that with A and B, okay? And I output X, right? So after this, I know X. I output X and I put this into a K, and I put the K, U equals to KX, right? So I just want to ask, okay, so if this is the output is Y, okay, and let's say input is our U, okay, so then now with this controller, how the plant behave? Is a plant behave? So I want to know the whole feedback loop. How is I want to place this 2 poles at -5 and -6. Okay, and from the stability lecture, you know this is stable, right? So you have 2 poles that you have 2 poles at both of them are negative. This is a continuous time, so this should be stable. So that's let's see. Let's practice. Okay, so how to do that? So basically, you say, okay, so now let's first see what is my this is a transfer function. Okay, so what is my this characteristic polynomial? So this is supposed to be, okay, so how to compute this? So that should be your polynomial, that should be a determinant of, say, that should be I minus A, right? So that's a characteristic polynomial. Then this will be determinant of, so I minus 1, I minus 2, minus 3, minus 4. Okay, the determinant of this guy. Okay, so then I got this I minus 1, I minus 2, minus 12. Okay, so then this equals to I squared minus 3s. 1 times 2 is 2, so minus 10. Okay. So this is what we got. So this is our current, this is for the plant, this is our plant's characteristic polynomial. So I want to make this to be our desired characteristic polynomial will be minus 4 and minus 5. Right. So in this case, what we can do. So then our desired polynomial will be just s plus 5 and s plus 6, right? So then the two roots are minus 4, 5, and minus 6. So this will be s squared plus 11s plus 30. Right, so that's what the 2 lambda we want. So then that's equals to lambda 1 equals to minus 5. Lambda 2 will be minus 6. Okay. So then what we do, so given what we learned in the last lecture, so we want to say, okay, so we can use a controllable canonical form to do this. So in the controllable canonical form, we say we will put this polynomials. So if this is our current characteristic polynomial, then what is our controllable canonical form, right? So we can directly write out this equals to, say, this is a 10, right? So minus 10 will be, minus 10 will be 10, and 3 is 10 come to here, 3 come to here, right? So that's A0, A1, A0, A1, and 0 and 1. So that's our A. X plus B is always a 0, 0, 0, 1, U, right? So that's here, that what we get. So A0 minus A0 and minus A1. And B is just 0, 0, 1. So that's realization, that's our controllable canonical form. Okay, so then we say what we do is the U is just a B. That's our this is our A tilde and B tilde. Okay, so that's our controllable canonical form. So then we compute a K tilde. So we directly, so first we convert, so this we have a system A and B. We can go to the A tilde, B tilde, that's our controllable canonical form, right? So via a transformation M. And we, from here, we can design a K tilde that is, our desired K to put the system to be, so lambda desired. And after we do that, we compute the real K. The real K, that is here. The real K, that is K equals K tilde M inverse. K equals to K tilde M inverse. So that's our plan. So now we got A tilde, B tilde. We can directly design the K tilde. Right. The K tilde is actually quite easy to compute. Let me see. Before that, I think we also need something else. We need the P. We need to, let's see, K here. Let's see. How do I explain? Okay, so here, this is our how we can get our K tilde. And this is also how we got our K tilde. K tilde is just follow this formula and make this formula to be this delta desired as. Okay, so after we plug in this K, so what we have the desired one is this. So we make this to be our desired one and desired characteristic polynomial, and we hope this one will be lambda s squared plus -3 plus K1 s plus -10 minus K0. So you can see here we augment this K1 to this -3, and we plus. So this should be minus K0. So we minus K1 and minus K0, so that we want to, after this original system, have this feedback control K. We have these two terms in the system, and we want this new system, this new feedback system, equals to the desired system, desired characteristic polynomial, which is what we want. So from this equation, we can compute what is a K1 and what is a K0. So here 11 equals to -3 minus K1, and 30 equals to -10 minus K0. So K1 equals to 14 and K0 equals to 40. Right. So this is what our new K. So if we have this then should have a tilde here because this is still working in the poly. So our K tilde equals to K1 and K -40 K0 and minus let's see. Oh, though I forgot there's a minus sign, so that should be -40 and -40. So that's a -40, 40. Okay, right. So you move this to the other side. That's a -10, -30. That should be -40. Okay, so that's our K tilde. So with this K tilde, we so this basically this is a way. Let me repeat. So you have this this original system, and you calculate the polynomial characteristic polynomial, and with this characteristic polynomial, you have you have this feedback, because the characteristic polynomial has a very unique form. So this form. So and the B is just 0, 0, 1, right? So B is 0, 0, 0, 1, and K is only a row, right? K tilde is only a row, and when K times B times K, so you have, so this guy just equals to nothing but all 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, except that the last row is k0 tilde, k1 tilde, until kn minus 1 tilde. Right. So this is bk. And if we add this bk to a, and this a tilde, so this is a tilde. So we add these two things together. You can see this bk0 is directly added to the all the last row. And this is what you get. And this is what you get because this is still in the controllable canonical form because all these ones are off diagonal, and you just only change this part. And these a's are the the denominator, the coefficient of denominator of the transfer function. So here we can directly modify the coefficient of characteristic polynomials, right? So the new characteristic polynomial is just with the coefficient that just with minus a0 plus k tilde minus a1 plus k tilde. So when you take the polynomial times a minus sign to here, and this is what you get. So this is our final characteristic polynomial in the controllable form, and you just need to compare this one with your desired polynomials, and you tune the k tilde such that you make this coefficient to be your desired coefficient. Okay, so now you are here, and you tune k tilde, and you make this your feedback system to be the desired feedback system. So calculate the k tilde. However, this k tilde is still in the it's only useful for the a tilde and b tilde, and we directly, this is in the controllable canonical form. So we want as k that can directly work with a and b. Okay, so our last step is we need to know the transfer similarity transformation matrix. So this M, or model matrix M. So this M can be computed, k tilde, M inverse can be directly computed by, so we know M equals to P and the PC inverse. Okay, to calculate this M inverse, so you get this inverse, and this should be PC times P inverse. Okay, so that we times this will be PC and the P inverse. Okay, so what is a PC? PC is a controllable controllability matrix for A tilde and B tilde. Okay, so let's compute PC. PC equals to B tilde A tilde B tilde, right? So that's our controllable matrix. So that will be B tilde 0, 1, and A tilde B tilde will be 1 and 3. Okay, that's our PC. And we need to compute the P inverse. Okay, so let's compute what is P. P is B, AB. Okay, so that B is 1, 1, here 1, 1, and AB is just A times B. So that's 4, 6. Okay, now we need to compute the inverse of this guy, inverse of P. The inverse of P is for any, this is a 2 by 2, so you probably know the formula. That will be, if this is ABCD, so that will be AD minus BC, and DA minus B minus C, right? So that's the formula. So that's if the P is ABCD, and we compute this one to be 6 minus 4, this will be half. Then this one will be 6, 1, minus 4, minus 1, right? So then now you times this 3 together. So K will equals to K tilde. K tilde is just minus 40, minus 40. So this should be a row. So transpose times PC is 0, 1, 1, 3 times half 6 minus 4 minus 1, 1. So this is what you finally you will get. Okay, so this will be so minus 1 minus 13. So Rachel, which, oh, I think I already corrected that. Okay, so yeah, this is what we get for this exam. Practice it one more time. So that I think you'll see this is actually very simple to see. Okay, so there's a bunch of math here. You know, if you get lost, you just again go back and practice this again. So, but I think more importantly, you know this this sequence. So what we are doing here, this is more important. The pipeline and the concept is more important. So I want to repeat this. So you give a system and you want to design your pose at some place. So you first convert this thing to the controllable canonical form, and you design K tilde under this controllable canonical form. Why we do that? Because in this controllable canonical form, K is very easy to design. So because your K is is a coefficient that can directly influence your characteristic polynomial. Okay, that's K tilde. And then after you get this K tilde from your desired, you compute your desired polynomial, you write out this your current polynomial. Oh, by the way, remember that polynomial, this delta function with the similarity transformation is the same. Right, so the characteristic polynomial for this is the same because similarity transformation doesn't change the pose. So it's only change how it represents the system, doesn't change the system, right? So that's called similarity transformation. So so that's why this is our desired one, this is our original one, and this is our feedback one after we add this K tilde. So we add K tilde to this -3 and -10 here, and we want, after we add this K tilde, this polynomial should be similar to the desired polynomial, such that we can compute the K tildes. So after we get this K tildes, we need to do a similarity transformation back to the original system. And to get this similarity transformation, we need to compute the controllable matrix for the old system and the new system. And the new system means A tilde, B tilde. Old system means A and B. Because we know A and B and A tilde, B tilde, we can compute this M, and we can directly compute what is K from this equation. So this pipeline is, I hope you can understand this. I think this pipeline is more important. Okay. So yeah, so that's it. So one question is, what if this system is not controllable? What if this system is not controllable? So then the first step broke, right? Will break. So the first step will break. So here is an example. So before you do the pole placement, you should check the controllability, because we rely on the controllable canonical form in the realization section to do this. So if the system is not controllable, means whatever how hard you try that, you cannot really change you cannot control the system, right? So you cannot change the pose, the pose of the system. So this is look at this system. So I think this is already in the Jordan form. It's a fully diagonalized matrix. So it's already in the Jordan form, and you have 2 Jordan blocks for the same eigenvalue. And from Jordan form, you know that your B hat should be the last row. Your B hat should be the last row of each Jordan block for that same eigenvalue. So that B hat will be 1 and 3. So this the first row, the first last row, the second last row for your each Jordan block. And this you have 2, right, Jordan block. So the rank of this guy should be 2 to make the system controllable. But this is a 2 by 1, so it cannot be 2. So the rank is 1, maximum rank 1, right? So maximum rank 1. So this is not the controllable system from Jordan form method. So okay, so if it's not controllable, then what happens? If I still want to impose this structure. If we still want to impose this structure, then what happens? Okay. So what happens is this. Let's try. If you want to still do that u equals to kx, then you plug in this u into the system. Then you get your new system to be, so that's called A, call this B. So x dot equals to ax plus b times u is a kx, right? This become a plus b k x, right? This is our new system. And I said because this is not controllable for whatever k you tune, that this our new a will not be influenced. So we'll try this. So that a is -2 plus bk. Bk is just k is just k1, k2. So bk is so let's say bk equals to k1, k1, k3, k2, k0, k0, and sorry, I think I do that. Let's do it step by step. So b is 1, 3, okay, and the k is just a row, so that will be k0, k1. Okay, so that will be k0, k1, 3k0, 3k1. Right, so that's our bk. And add that to a. Let's see. bkx. Let's see. That make a mistake. Let's see. First row times first column. The first row. Let's see. Wait, so I think there's a mismatch. Yeah, I think what I wrote here is correct. What was on the slide was wrong. So it should be, yeah, I think this is correct. Okay, so but anyway, so we can add a and bk together. So a is -2, add this k0, and k1 add 0 is still k1, and this is 3k0, and minus 2 plus 3k1. Okay, good. And then what we do is this our new, this is let's call it a hat. So that's our new system, right? So our new system is a x dot equals a hat x. So this is a hat equals this. And we know this new system, let's see, this is a new system here. This is just a dot equals a hat x. And we want to know that what is the potential eigenvalues for this one. So we do what? We do the determinant, right? Determinant of this guy, the lambda I minus a. So that we can compute all the lambdas. Okay, equals to, yeah, I think here I should put this to be lambda just to be consistent. So this s should be lambda in this on this slide. So s is also okay, but I think just to be, yeah, consistent. So we just want to calculate the eigenvalues. Okay, so here lambda I minus a. Okay, so that will be minus a hat. So that will be lambda I minus a hat plus 2 minus k0 minus k1 minus 3k0 lambda plus 2 minus 3k1. Right, so we want to calculate the determinant of this guy. Now let's how to compute the determinant of 2 by 2. So that will be a times d minus b times c, right? So that will be equals to lambda plus 2 minus k0. Okay, lambda plus 2 minus 3k1 minus k1 times minus k1 times 3 minus 3k0. Okay, so that will be, let's do one more step. So will be lambda plus 2 square. Okay, minus k0 plus 3k1 lambda plus 2 plus 3k0 k1 minus 3k0 k1. These two cancel out. Okay, so there will be lambda plus 2 and the lambda plus 2 minus k0 minus k3 3k1. Okay, so this is our final, this is our determinant of this a hat system. You can see whatever you do, you still have this, even you have two parameters, you still have this k0 and k1 in the same parentheses. So these two are coupled. That is to say that you can now independently change k0 and k1 and influence both eigenvalues. One eigenvalue, that lambda 1 will always equal to minus 2. Okay, so what happens when you have an uncontrollable system. So you have an eigenvalue that is fixed over there. Even you have this feedback system, those coefficients will clamp into one parenthesis, and you lose of control of your system. At least lose the control for this eigenvalue. So this eigenvalue will all be here. Here, fortunately, this lambda 1 is negative, so it's stable. So I think this so it's now controllable, but it's stabilizable, right? So, but if this is a positive, like eigenvalue, then this will be very, very hard to work with. Any questions so far? Okay, so there's a lot of mathematical equations, but the underlying concept I hope is clear. Okay, so let's continue. So let's go back to this slide, this figure, this review slide is really important. That we have these two systems, okay, and now look at this one and this one. So what's the difference between these two? You can see the difference is here we output the y, and here we output the x. Well, this is a plant, right? So you can now really control what you can output. And we assume that if y equals to x, if we can measure all the states, that would be great. However, a lot of times you can only measure something that is not directly the states. It's still observable, but you need to infer x from y. So this is what is a common problem. So for example, very common in the vehicle control situation, you can measure the longitudinal velocity, right? Because you know the spin speed of the wheel, and you will with that angular velocity or times the radius, that is basically roughly a velocity of your longitudinal speed for the car. However, to the lateral side of the car, it's not clear how to measure that, right? So you can still measure longitudinal velocity. You can also measure something like your angle, hiding angle. Okay, hiding angle, you can use some magnetic field. Say, what's my hiding? According to, because the Earth has a magnetic field, you can use a magnetic parameter, like a magnetic detector to measure what's your relative angle to the say north. That's possible. But for lateral velocity, you need to use your longitudinal velocity and your hiding angle to infer your lateral velocity. So that in this case, if your system, if your x has a lateral velocity, then you can now directly apply this feedback pole placement control. So actually, you only have y. This is a reality. So then what to do? Then this is what we'll do. This is called a controller. And from y, we want to infer x. This is called observer. This is called observe. You want to observe your state. Control, you want to control your state to a desired state. Observer, you want to observe your state. You observe y and infer your state. Okay. So then let's say how we can design an observer. This kind of observer is called it's also called Lunenburg observer. Lunenburg is a Stanford graduate, kind of a very smart. I think he published a paper like I mean around 20 for this algorithm. Yeah, so basically that's the situation. So we cannot observe the x. So here, so why not just use this? Why not just use the this system? So basically what it says is, okay, so you have a plant, you have a u, and you have a measurement y. Okay, so you want to have some feedback control so that you want to have say you want to have x inside, right? You want x times a gain to have your u. So you have a gain, that's the k, and you want to x into it, but you don't have x. So you want y to infer x, but why not just say I have another model that's a p, just a mimic of p, okay, and then I also input a u into this p, because this is a mimic one. This is like a simulation. So I can output anything I want, right? So I can output this x tilde and put this x tilde back to this x. Use this x as x tilde. So what's the issue of that? The issue is this p, while you have like a tilde, b tilde, c tilde, d tilde, that's your simulation, may not be equal to the real ABCD system. So if you blindly follow that, you will have trouble. It's more like you walk and you say, okay, so let me close my eye and I like use my brain to make a model of myself and the environment. And then, you know, whenever I give input, I can use my brain to calculate what's my potential, say, what is my predicted like position. Then I use that predicted position, which is your x tilde, that's your imagination, your say prediction, and use that to control. You probably can do that in a very short distance, maybe 2 meters. That's still fine. But if you do a long-term prediction or you run it for a long time, this error will propagate, and eventually you will lose your control because you're just too wrong from even though x tilde, b tilde, c tilde, d tilde are close to ABCD, but if you run it for a long time, you still have a problem. So that's a good idea, but it's not practical. So we want to modify this a little bit. So what we do, is as follows. So we can do this. So let's say we still have this x tilde. That's our, what we want from this estimation. Will equals to a x tilde plus b u. Okay. So this you can say this a tilde b tilde. But for simplicity, for now I just say use a and b. But you know that in the real world, that this a may not really represent the real world. Okay. Then how to remedy that is this. You could do a feedback control, another like a P control, and you see, okay, let's measure y and the y tilde. So what happens is this. So let me go back to here. So what happens is this. So because I know this P tilde and P has small difference, and I want to correct the difference. So what I do is I say I take, because this is a simulation, I know whatever I run. So this I can have this y tilde. And I can also output this y tilde, and I compare this y tilde with x tilde. So I have this minus plus. So this is our error of y. Let's call that EY. Let's call that our EY. This error of y. And I just input this back to the system. So we gave this EY. Okay. So we gave this EY. Let's see. Or I can do this. So I gave this EY, this is a little bit awkward here, back to this P tilde, back to this system. So what happens is, okay, so I know this EY, if this EY is small, is a 0, then I can trust my x tilde because I predict the same thing as the real world. But if this EY is different from this, if this EY is large, that means my y and y tilde is different. That means this two system is already different. So I want to use this error of y to drive the x tilde to x. Okay. And essentially how you do that is this. So you just times again and you drag it to and plug this one to the whole system. So if this y is larger than this y tilde, then you want to come back to this x and say, okay, increase x, because your y tilde is smaller than your real world, your measurement of y. So you need to want x tilde to be larger so that y tilde also could be larger. Okay, so vice versa, so that also follows. Okay, so this is like a simple feedback control again for y, and we can do some derivation on after that. So it's x tilde plus bu, because we know what is y, right? So plus L Y is your measurement, and Y tilde is nothing but Cx tilde minus D U, right? Okay, so then we can do another derivation. So that'll be A minus LC X tilde plus B minus LD U plus LY. Okay, so this is just some linear algebra. Then I define E that equals to be X minus X tilde. So this because this is a system. This look, you can see this looks already a little weird. It's not in our ABCD matrix form. So let me simplify that. So I define E equals X minus X tilde. So what happened is I can test E dot equals to X dot minus X tilde dot. X dot is just AX plus BU. Minus X tilde dot is just plug in what is here, right? Plug in here. So that will be minus A minus LC X tilde minus B minus LD U minus LY. Okay. So do some simplification again. So Y is just Cx plus du. Okay. Do some simplification so that you can see X. We have A. We have X tilde. So here that should be A X minus X tilde, which is just E. Okay. Plus U, combine everything about U. So BU and this minus BU, so this cancel out. So that will be so this BU okay. So B minus B plus LD minus LD, right? So that's everything about U. That's everything about U. So this is fully cancel out. So how about everything about this X? So that will be X will be A minus LC, right? X. And how about X tilde? That minus A minus LC X tilde. Combine these two, so that will be A minus LC. X minus X tilde will be E. Okay, so then the final just X dot equals to E dot equals to A minus LCE. So that's our final dynamics. In other words, the only dynamics is governed by this A minus LC for our observer. So nothing to do with B, and it's only controlled by L. So this is very similar to the controllability that we only have that A plus BK. Right, so that's our controllability matrix, the final matrix for that's A tilde. So this is our new system dynamics for E. And similarly, we can also convert things to the observable canonical form. So recap, this is our observable canonical form. That C is in a very nice form. So if A minus LC, L is just a column. So LC is just a matrix. So LC will be equals to this A is fully only have this column. The first column has a value, a real meaningful value, and the C is just a row with only the first column being 1. So L is a column, so with the L0 to L minus 1, right? So we can then if A minus LC, so this is L, this is a C, right? So we can combine them, so that becomes something like only Ln minus 1 tilde with a 0, 0, 0, and L minus 2 tilde, that's with all the zeros. Until L0 tilde with all the zeros. We can directly add this one to the A tilde. So this is our final A. This is our final A. So the new A with the feedback control. Let's call it A head. So we can achieve arbitrary pole placement where L tilde, as long as this is observable, so that you can have this form. So similar, that will be quite similar to, and then we can compute M to transform that L tilde to L. So that's the same as the before. And we will practice a similar example as we did for the controllable canonical form. So here, this time I'll do that a little bit fast. So still the formula is similar. So basically we say, okay, so we have a design observer for A and C. So that basically is I said that means X dot. Our original system will be A, right? X. B doesn't matter because B doesn't shows up. That Y equals to CX. And D also doesn't matter because those all cancel out. So this is a system. I want this the final system, the X. Our final system that will be E will be E dot equals to A minus LC. E, I hope this system has eigenvalue to add minus 10 and minus 20. So basically this is our requirement. We given A and C, and we want to compute what is L. Okay, so still the similar way. So we will so we need to do the following. So we need to compute the polynomial, our current polynomial for this A, and we also want to compute our desired polynomial for this minus 10 and minus 20. So our current polynomial will be the determinant of lambda I minus A equals to determinant of lambda minus 1, 3, 4, lambda minus 4, right? So that will be lambda minus 1, lambda minus 2, minus 12. Okay, so this will be I squared minus 3 lambda minus 10. So that's our desired polynomial. That's our current current eigenvalue and current polynomial. And our desired one, or feedback one, desired feedback S equals to the, we already know this desired polynomial. So that will be roots of the polynomial. So that will be lambda plus 10, lambda plus 20. Okay, so that'll be lambda square plus 30 lambda plus 200. Okay, our feedback polynomial can also be expressed by our feedback can also equation can also be described by this. So that will be lambda square plus minus 3 plus L1 tilde lambda plus minus 10 plus L0 tilde. Okay, so that will be our feedback with L. So this is our desired polynomial. So this is our feedback from this one at L. with the L feedback, we can change this system to this. So we want this to be equal so that L1 just becomes 33. So L1 just becomes 33. L2 L0 will become 210. And so you make this equals to this and this equals to this one. So they have L0 tilde and L1 tilde. Okay, so our L equals to 33 and 210. Okay, we still need to compute what is real. It's L tilde. What is L? So the L equals to ML tilde, right? So we want to compute L tilde. So M equals to Q inverse Q observer. So that and times L tilde. So this Q is just CA. That's our original system, right? And the Q tilde will be inverse C tilde CA C tilde A tilde L tilde. Okay. So with the characteristic polynomials, you should be able to compute this C tilde A tilde, and this AC was already given, and L tilde was computed in this way. So eventually you can compute what is L. So we won't do the calculation here. Okay, so that's basically what happens. Just one more slide. So you can write in this form in a different way. So that our x tilde dot equals to ax tilde plus b u plus feedback that y minus y tilde. So that's our how we design our observer, right? So you can also write in a different way. That will be ax tilde. So this additional term is not in ABCD format. You can do that in ABCD format. That's B concatenate with L, then times basically this you can compute with U with y minus u tilde. Okay. This is contained in this way. Then this will be y observer will be say x tilde y tilde. You need both to do the observation. So that will be in x tilde. So that will be c plus 0n du. So basically you have this A, B, C, D matrix, right? So your state is x tilde, your input is a u and a y minus y tilde. So if you remember what I draw previously, so this is our input. This is our input, and this is our ABCD matrix. You can also augment this input to be here, write this to be u and y minus y tilde, but then you have another 2 rows of zeros, 2 columns of zeros. So and this is our observation is just x and x tilde and y tilde. So you can see this is the same thing I draw previously with this figure. So our input is EY, that's y tilde minus y minus y tilde, and this is u. So that's our two input. We concatenate that into u y minus y tilde, and the output is just x tilde and y tilde. So I can write things here again. So that x tilde dot equals to ax tilde plus bl concatenate. So that's our b, and then u y minus y tilde. So that's our this concatenate thing will be our new u, and the y just output is just x tilde y tilde equals to inc. That's our new c, x tilde plus 0n d u. So this is what this system does. This is our observer. Okay. Any last minute questions? So in today's lecture, I think we review our controllability canonical control the pole placement for controller, and also we say the same algorithm can also apply to design observer. In the case that you don't have x to direct feedback to the system, you use y to infer the x, and then you get x tilde. So now you get x tilde. So you do this, and now this become x tilde. So you just use x tilde to feedback to the system. Then everything will work out, and you can tweak how fast is your observer by tweak L. You can tweak how fast your controller with a K. So you can, and here you have a L to control the how fast you want to do the feedback for the observer. Any questions? Feel free to ask.
Professor?
Yeah, go ahead.
I have a question on slide 2022.
Okay.
I think it's 20. Yeah. So for when we substitute y tilde as cx tilde plus du on the second line of the equation.
Where?
Minus cx tilde minus above.
Here?
No, two lines above. Yeah, above that one. Yeah.
Okay.
Y minus cx tilde minus du. Below that.
Here. Okay. I see.
Yeah. So why is this c just like original c, not c tilde? Because it comes from the
okay.
y tilde. Why is that?
So it should be c tilde and y tilde. You're right. And actually, this should be a and tilde and b tilde. But we say this is a and b and c and d for a very short period of time. They are very close. They are very close. And because you have this feedback, and I think that effect can be removed. And just for convention, that people use a, b, c, d, so that you can do some cancellation things. So in theory, yes, you have a c tilde, but we say c tilde and the c are very similar. But if you close your eyes and you do that for a long time, you'll have problem. If you have this feedback, that will be gone.
Okay. Yeah.
So yeah, I think this is a very good question. So I didn't realize that when I was a student, and later on I found out this is the case. Yes, you're right. There should be c tilde and d tilde, actually a tilde, b tilde. But because of the feedback, and you have the confidence to make them, and they're actually, we assume they're similar. But if you don't have this feedback, you don't have these feedback things, for a while you'll have a problem. For a short time period, you're okay. And when we plug in this here, because this is a feedback system, you can stabilize the system. So so that still for a long time you're okay. You're far away from the unstable zone. The Zoom recording page on Canvas appear to be empty. I think I received some email that they will not allow to do this anymore. But I think I will upload that to the YouTube link. The YouTube link is on the Canvas on the syllabus. Jikai, does that make sense to you? Okay. Yeah, I think okay, so someone asked a private question. So I think, yeah, the Zoom link on the Canvas is gone because I think there is some issue between Samuel and Zoom. And I will still upload things on the Canvas. Okay, thanks. Good luck for your midterm on Thursday. And I'm looking forward for you guys to work on the project. Okay, bye.